Okay, so I'm very happy to introduce Şölen Kumbay Yıldız, a very close friend of mine. She is an associate professor in the Department of Electrical and Electronics Engineering at Hacettepe University. She received her BS, MS, and PhD degrees all from the same department, where she has been actively involved in teaching and research since 2004. Her research interests include control systems, modeling, system identification, soft sensor development, ionospheric modeling. She spent a year as a postdoctoral fellow at the University of Wollongong in Australia, I don't know how to pronounce, working in the School of Mechanical Materials, Mechatronic and Biomedical Engineering. Dr. Yıldız currently focuses on exploring innovative applications of soft sensor in autonomous robotics and biomedical devices, alongside tracking ionospheric model parameters using spatio-temporal Kalman filtering.
Good afternoon, everyone. I would like to start by thanking you for the opportunity to present here today. Like my colleague and friend said earlier, I will today present some of my research regarding soft sensors and their applications in various fields. Soft sensor systems, their fabrication, their use is part of my ongoing research. Now, by nature, this is a cross-disciplinary field, ranging from prosthetics to robotics to posture sensing and biomedical systems. Even though it is not the central focus of today's presentation, I also work on modeling the mid-latitude ionosphere, but perhaps that can be the subject of some other meeting, some other get-together. So today I will mainly discuss and explain soft sensors, their fabrication, and some applications. As I mentioned, this is a cross-disciplinary field. It has applications in robotics, in material sciences, brings together biomedical engineering, obviously electronics and signal processing. The main workflow is, as you can see here, we start off by fabricating our own sensors. We try modeling them, use various signal processing tools, and then try to validate by bringing together different experimental setups. Now, obviously, there is an ongoing loop between these steps. This is a closed loop procedure. At every step, we go back to the design and fabrication phases in order to suit the sensor to the problem at hand. Obviously, this type of study brings together various people across several academic disciplines. Among them, neuroscience, biomechanics, and control systems can be listed. We also try and work closely with industry partners. Obviously, everything also serves in the bringing up of experienced engineers and hopefully academics as well. As an overview of applications of soft sensors, we can list autonomous robots, wearable devices, rehab and prosthetics, posture monitoring among them, physiotherapy, biomedical instrumentation, and human-machine interaction. I will try and give examples from most of these fields. But first of all, I would like to start with the question of what are soft sensors. Well, soft sensors are sensors made of deformable, compliant materials, usually stretchable materials. They can be used to detect various variables, particularly strain, pressure, bending, and curvature. They are usually made from elastomers, conductive liquids, which we usually refer them to as microfluidic sensors. Their importance can be summarized through a few points. first important property would be their mechanical compliance. Unlike their rigid counterparts, they can conform to the soft and curved surfaces. Their stretchability and flexibility make them ideal for very dynamic environments. They are obviously very lightweight. They can be used to sense various variables. There is a huge amount of choice, actually, regarding the use of materials. The geometry is very flexible. They can, like I said, be made of various different materials, including biocompatible materials, which also happens to be a big advantage. Now, my work with soft sensors has actually begun with my visit in Australia, where I was a visiting scholar. There, I have started experimenting with fabricating soft strain sensors. In the earlier work, I have tried two different approaches, actually, which I try to summarize here on this slide. Well, first things first, I have used two main different base substrates. They are both silicon rubbers. These are the brands that I have used. There is a distinct difference between the two. One of them is very soft. It has a Shore hardness of 0.030, very soft. The other one is much harder. It has a Shore hardness of, if I remember correctly, around 20. So, huge difference in them. In order to make the sensors have electrical properties, we use electrically conductive liquids. Two versions are listed here. One of them is a carbon black dispersion. The other one is or contains carbon nanofibers in PEDOT-PSS. Now, one of the fabrication methods involves obtaining two thin layers of silicon rubbers. This can be accomplished using a spin coater or a microfilm applicator. Then one of these layers is patterned with the help of a laser, such that it has a microchannel engraved on it, resembling the shape of a strain gauge. Then the two layers are treated using plasma and then immediately brought together such that they can bond seamlessly by trapping the engraved pattern in between the two layers. So when this process is complete, you have microchannels trapped in a single uniform silicon structure. Then when these microchannels are ready, they are filled with one of the electrically conductive liquids with the help of syringes. Another alternative of fabricating a similar structure involves 3D printed molds. Once a mold is created, then silicone rubber is used to fill these molds. Then once the silicone has cured, a second layer is created, and then the two layers are brought together before the second layer cures completely, so that when the process is once again complete, you have microchannels trapped within the structure, which then can be filled with an electrically conductive liquid using syringes. Here you can see the shape of the pattern inside the sensor, and this is an actual finished sensor with the liquid injected inside the channel. So this is basically a strain gauge. Before using this as a sensor to sense strain, obviously we have to go through a series of tests in order to measure the performance both quantitatively and qualitatively. Now, the quantitative analyses are meant to analyze the sensor's behavior in terms of linearity, hysteresis, resolution, and response time. Now, with the materials that I have mentioned earlier, the two substrates and the two liquids, at the time I have prepared 3 different sensors, all with the same geometry, but different base, substrate, and liquid combinations. And then I have gone ahead and tested them by applying different amounts of strain and measured the resistance change. Now, obviously, these work like actual strain gauges. As the channels are deformed, the electrical overall resistance changes. And if the deformation causes the channels to become longer, naturally, the resistance increases. The point is for us to see if the change of resistance and change of strain, change of applied strain, vary linearly with each other. Now, the tests have confirmed that all the choices of materials, all the combinations that we have considered, they present a more or less linear relationship between change of resistance and applied strain, which is a huge bonus for us, would be a huge plus. This performed actually better than our expectations. We also measured the gauge factor, the relationship constant, if you will, between applied strain and change of resistance. And for all these sensors having the same geometry, the gauge factors were around 2, which was also great for the time. Now, hysteresis is a common problem with compliant structures. In this case, hysteresis corresponds to the fact that when you stretch the sensor and then when you release it, do the change of resistance values overlap with each other, or if the way back is kind of different than the way forward? Well, according to our test results, we have confirmed that the softer the base material, the less hysteresis you end up with in terms of measurements. So the two cases in here have the softer silicon substrate as the base substrate. Therefore, they display less hysteresis in their behavior. Turns out this was not expected. The liquid used inside also affects the amount of hysteresis to some degree. As you can see, the carbon black dispersion and the soft silicon base substrate resulted in significantly less hysteresis than the others. Then there is the question of resolution. How capable is a sensor of producing a different reading by how small a change applied in the applied strain? Lucky for us, all the variations that we have tried provided a resolution below 1%. Then finally, we also observed the transient response. To do that, we applied a sudden strain to a sensor at rest, and then we observed the change of resistance, and then the strain is, after some time, dropped suddenly back to 0. Once again, the change of resistance is observed. Turns out the softer base substrate also provides a faster step response. It has a much smaller time constant. Therefore, we can conclude that softer silicon rubbers are better suited for applications where the mechanical stimuli tend to change more abruptly. So, working with soft strain sensors obviously has some pros and cons, some advantages, some disadvantages when compared with their rigid counterparts. Now, the fabrication cost to make a soft sensor is really, really low. I mean, the substrates, the materials are cheap, so you can make hundreds of them for a very low price. They also remain operational at very high strains, which is the biggest advantage there is, because the rigid counterparts, a rigid strain sensor, I don't know, can it measure any strains over 3%, 4%? Is it possible for a rigid strain gauge? Hardly, I would say. However, you have seen in the previous graphs, some of the sensors we were able to stretch up to 100%, which is a big difference when compared to the rigid ones. It was great that we observed a linear relationship between change of resistance and strain. They had very good, very low, very high resolution. Some of the combinations displayed a very small time constant, which is also great. And we also know the sensor geometry can be changed very easily. It's all in our hands. These being the advantages, of course, there are a few disadvantages as well. First, there is a high wastage during fabrication. Although the wastage kind of drops as you get more experience, as you spend more time in the lab preparing these sensors, but still some of the sensors end up being trashed before even getting used in any application. There is one problem that needs to be still addressed. Although the sensors remain operational for a reasonable amount of time, after a while, the liquid within the sensor is being absorbed by the silicon substrate, which eventually renders the sensor inoperable. Sometimes it takes weeks, sometimes it takes months, but eventually this will happen. Also, placing of the wires to measure the resistance is or may be kind of problematic depending on the setup they are used. Speaking of lab-made soft sensors, there are a few commercially available soft sensors that are capable of measuring strain. But the microfluidic ones, the fabrication of which I just tried to explain, they are not commercially available. I think this is pretty obvious why, for the time being. The fabrication procedure still needs work for them to become commercially available. But here you can see some examples. So the most common ones, I think, are the ones that are shown here. These are actually electrically conductive rubber cords. So these being the most common ones out there, we decided let's compare one of them with our own sensors. Then remember the experiments that I explained earlier. We repeated them with the commercially available rubber cord as well and compared its performance with ours. Turns out the ones we made in the lab have less hysteresis, which is good. They have better resolution, the ones that we made, at low strain levels, which is also an advantage. And the maximum strain that can be applied to the commercial soft strain sensor was at 50% at maximum, while ours could be easily stretched beyond 100%. Also, in terms of time response, the commercial sensor has way worse time characteristic than the ones we made in the lab. So, having gotten to know our sensors and their behavior so well, this encouraged us to put the sensors to good use in some test setup. At the time, one of my colleagues was working on a soft prosthetic hand. So it looked kind of a good idea for me to test the performance of the sensors I had just fabricated at the time. So we took one of the fingers of the prosthesis, because that's where he started anyway, and we placed soft strain sensors on each of the 3 joints of a prosthetic finger. Now this finger, this is an interesting structure actually. It is what we call a monolithic structure. It is printed using a 3D printed from a soft material. It doesn't have revolute joints. Instead, it has flexure hinges which serve as joints, and it is actuated by a single simple string that runs through the prosthetic finger. So even though with 3 joints, this is an under-actuated system because there's only one string to bend the finger. So the objective was to employ the strain sensors and to see if we can control the tip position of the finger by just using the feedback received from the soft sensors. So in order to do that, first we made a series of experiments. We recorded resistance values from the sensors at various different positions. We recorded joint angles, and then we tried to estimate some relationship constant, some matrix between the change of resistance of the soft resistors and the joint angles. This right-hand side figure compares the goodness of this estimation. You can see the red and black dots more or less overlap. One of the set comes from actual readings from image processing. The other ones are the estimated positions. More or less they overlap, which gave us hope actually toward achieving closed-loop control of the tip of fingertip position of this prosthetic hand. Here, on the right, you can see the experiment results. You can see the dashed line represents the reference that we applied to the overall system, and the blue line is the fingertip position, which is controlled, I repeat, only from the feedback of the soft sensors. Nothing else has been utilized for this experiment. Now, at the time, actually even now, this is a pretty huge accomplishment, because even though the work on soft sensors has been going on for a while now, maybe 15, 20 years, closed-loop applications, closed-loop control applications, still not many of them out there. And this work is a few years old already. At the time, there were no closed-loop control applications by using the feedback from only soft sensors. So this was a great achievement, and it brought our hopes really high for further uses of our soft sensors. So from this point on, I would like to give you other examples where soft sensors can be employed in a more summarized fashion. Here you can see a data glove which is made functional with the use of those rubber cord sensors, the commercial ones. The ultimate objective was to display Turkish Sign Language alphabets onto some screen or mobile platform using the data received from the sensors on the glove. Along with the rubber cord sensors, my project group has also utilized IMUs, obviously, because the orientation of the hand was also necessary, but that isn't the exact focus in this application. The point is, the soft sensors performed actually really well, all the letters. The students were able to display and catch all the letters and display them on the screen via Bluetooth using just the gloves. Turns out there is a distinct difference between Turkish and English Sign Language, by the way. Turkish Sign Language requires the use of two hands. Therefore, they had to build an auxiliary glove with pressure sensors, with touch sensors actually, made with electrically conductive thread, which in my book still counts as soft and compliant sensors. Now, a similar application was then conducted by another student of mine. Now, the previous one was a data glove using commercial sensors. So this student of mine tried to fabricate first his own sensors, soft strain sensors, and then create a motion capture glove in a similar way. You can see the homemade sensors. These are actual photographs. You can see them on the glove. These are the sensors he built first, he fabricated first in the lab, and then used in his application, which also performed really well. So this was also very encouraging for our future work. All right, this is a more recent endeavor. Well, the idea came to mind. This is as the result of the recommendation of my friend and colleague, Dr. İsmail Uyanık. Seeing our sensors, he suggested perhaps we can change their shape such that they can be used to mimic the insect antenna. In particular, the objective was to mimic the wall-following property, if you will, of the American cockroach using their antenna. That was an interesting recommendation, actually. So we said, why not? All we needed to do was change the shape of the sensor such that it kind of resembles a bug's antenna, that is longer and narrower in dimensions. The fabrication procedure more or less remained the same. However, we did make a change on the way. We changed the liquid that we used. Remember the problem of the liquid being absorbed by the substrate? Well, we used another liquid, carbon grease, in order to solve that problem, which is a more viscous liquid, by the way. Well, using this conductive liquid, the sensors we have observed remained operational for months, which was a great big jump, actually. Anyway, so we made bugs antennas, which this time they are not used to measure strain, but bending or curvature angle. So the sensors we made, turns out, could be used in a two-way fashion. When you bend them one way, the resistance decreases. When you bend them the other way, the resistance decreases. This was obviously intentional. We made the microchannels closer to one surface such that we could differentiate between the direction of bending. So this was also another plus we hadn't thought about before. So with the sensors fabricated, we came up with a test platform in order to measure or observe their performance. You can see the test platform here. It has a test car which runs on a linear track along a wall, if you will, with different profiles on it. The soft antenna is placed to the side and comes in contact with the varying shape of the test wall. So this figure represents the shape of the wall used in the tests. You can see here. And the top plot shows the change of resistance of the sensor. As you can see, there is a very good relationship between the distance of the car and the wall and the change of resistance of the sensor. Once again, the results were very encouraging, so we decided to move to the next step. We built a very simple autonomous robot. We placed the sensor as if it were the antenna of the bug, and then we tried and see if the cockroach's wall-following behavior can indeed be accomplished with this sensor. Now, hopefully, this will play. I'm not sure how this is going to work. Like this. Now, as you can see, the bug is the robot, the autonomous robot, is capable of following the outer surface of this test platform by using only the feedback received from its antenna. So yeah, mission accomplished. I must say though, this video is sped up by a factor of 2. Okay, normally the operation is twice as slower, as you can see. But in the end, the results, yeah, were very, again, encouraging. So wall following achieved. What else could we do? Well, the sensor behaved and the sensor performed really well. Exceeded our expectations. So we decided to get to know these sensors a little closer. So what we did was alter the test platforms, test walls, sorry. We subjected a series of sensors to different profiles of test walls, each of them in a sinusoidal shape, having different periods. Recording the sensors, we observed both in time, their responses, and then using the time responses against varying periods of sinusoidal walls, we were able to obtain their frequency response as well. Now, what this analysis taught us is the following. Now, each sensor obviously results in a more or less different value in resistance change. This is to be expected. These are homemade sensors. Even though the geometry, or even though they come all from the same molds, there will be obviously mistakes, faulty demolding processes, impurities within the mixtures, etc. Also, the channels are filled by hand using syringes. There is no way you can guarantee each sensor has an equal amount of liquid inside the channel. So this was to be expected. The important thing is, regardless of the differences, at each frequency, the magnitude and phase behavior of the sensors were similar. You can see the peaks and the troughs, they are all consistent within different sensors. Are they perfect? No, they are not. But we had already shown a few applications where they can be relied on. So, having gotten to know our sensors even better at this point, and loving the idea of the Bugs antenna, we decided to put it to test using yet another approach. Perhaps you are already familiar with the family of bug algorithms. They are widely known obstacle avoiding approaches in robotics. Obviously, there is nothing new regarding bug algorithms in this study. However, the point here is, can we apply these bug algorithms relying only on the feedback received from a soft antenna? That was the challenge. To that end, we have prepared a test environment with two obstacles in custom shapes. We have our little bug robot here, equipped with soft sensors. There is a difference. It has not one but two sensors this time, one on the side serving as an antenna, one in front to detect collision with an obstacle. Also soft, by the way. Same sensor, different geometry. And we tried to see if these bug algorithms indeed can be accomplished using the soft sensor feedback. So here I have two examples. Okay, not like this, maybe like this. The first one belongs to the bug1 algorithm. According to this algorithm, the robot has to traverse the entire obstacle first before moving on to the next one that is closer to the target, which, as you can see, does so using the wall following behavior we discussed earlier. Once the first obstacle is done, moves on to the second one, traverses it entirely, then finds a way towards the target, the best way towards the target actually, and then goes on its way to the target point. The graphs here, the top graph shows the input received from what we call the bumper sensor, the one that detects collision only. Here you can see the blue line, which represents the signal from the soft sensor. For confirmation purposes, we have also equipped the robot with an ultrasonic sensor. The red line represents the data from the ultrasonic sensor. Now the second one shows distinctly the difference between bug1 and bug2 algorithms. Here it takes less time, obviously, for the robot to travel to the target position. As you can see, again, mission accomplished. Only soft sensor feedback has been used for the navigation purposes of the robot. Now, obviously, the scenarios can vary. It can be used in other robotics applications along the way. We will think of a few in the future, hopefully. Speaking of other applications with flexible sensors, these I'm sure some of you are already familiar with. These are commercially available flex sensors. They still belong to the family of flexible electronics. Not entirely soft, obviously. They cannot be stretched, but they can bend. We are actually still working on a little project in which the students are designing a vest that can be worn by an otherwise healthy person, by the way, who may or may not have poor posture. I mean, who don't, right? The objective is to warn the user should the posture becomes poor for a prolonged time. That's the purpose. To that end, my students have placed 1, 2, 3, 4 flex sensors to key positions at the back and lumbar spine positions. And like I said, the objective is to warn the user if the posture becomes poor for a prolonged time. Once the project is complete, I will be happy to show you the end results. Here is another application, although similar. This is a little more sophisticated than the previous one. This work is actually part of a much larger project. The large project entails a telerehabilitation system for DMD and MS patients. These are genetic diseases. Recovery is unfortunately not possible, but these patients require extensive physical therapy, and sometimes going through physical therapy for so many times in the hospitals becomes really challenging. So the project essentially helps these patients to go through some parts of the therapy at home in their own comfort. As part of this bigger project, one of my grad students is working on designing a jacket, which is once again equipped with flex sensors as well as IMUs to help in these physical rehabilitation, in a series of actually physical rehabilitation postures and gestures that were provided by the physical therapy department, by professionals from that department to us. The objective is to verify that the user or the wearer of the jacket is capable of performing the tasks or not. Well, to do that, we have employed a series of machine learning algorithms by using the data received from those sensors. Well, currently, our studies have shown the flex sensor data, particularly when it is put into these algorithms, these machine learning algorithms perform more or less similarly. As you know, these are the confusion matrices. The diagonal elements show us the correctly identified and classified gestures. Turns out, for the time being, using our algorithms, the random forest approach results in the best performance so far. But like I said, this is an ongoing process. We will see if we can improve upon these results even further. Here you see one last example where we have employed soft strain sensors. What you see here is a device that is called a cell stretching device. Turns out this is a widely used device in laboratories in order to test the effects of mechanical strain on cell cultures. Apparently, mechanical strain plays a really important role in these analyses. And the devices that are currently available commercially, they do not come with a version of closed-loop control, if you will. Now, how the device operates is this way. There are 4 motors, as you can see. In the middle, a membrane is placed, on which the cell cultures are planted, and the device applies different values of mechanical strain over very long times, either on one axis or on both axes. The point here is, by the way, the whole project is supervised by Dr. İsmail Uyanık. It involves building the device from scratch as well, but where the soft sensors come into play is the fact that these devices are usually operated in an open loop fashion, like I said. So we have these soft sensors. Already a soft membrane is used within the operation of this device, so why not bring the sensor and the membrane together so that we can obtain feedback from the sensor and achieve closed loop control of the motors instead of operating the whole device in an open loop fashion. So that is what we did. Once again, for the problem at hand, we easily changed the dimensions and the geometry of the soft sensors. We fabricate in our lab like this. We place them on the device and then started applying various degrees, various percentages of strains over a certain amount of time. Now the initial results have shown that there is a direct relationship between the applied strain by the device and the change of resistance from our sensors, which once again gave us great hope towards accomplishing closed loop control. In fact, we already have some results which show closed loop control based on the feedback from the soft sensor is quite possible in controlling the device. I haven't shown those results here just yet. Again, like I said, this is also an ongoing process, but I wanted to include it here as a different application area, a biomedical device, if you will, for the use of soft sensors. So, obviously there is plenty of work to do in the future. We are still improving on the design and fabrication of soft sensors. There are still a great many materials that we haven't worked with, that we haven't tried. We still have various other liquids to experiment with, which we are hoping can improve the sensor performance even further. We can think of many other biomedical device or robotics applications where soft sensors can play a crucial role to make them operate safer around humans or any other living being for that matter. Like I said already, there are still a few challenges left to be solved, which can be again addressed by trying different materials and different fabrication methods. But like I said, we are still full with ideas, and hopefully there will be other opportunities for me to present them. So I would like to thank you for listening, and I hope I was able to express the importance of soft sensors in various different structures and systems and application fields. If there are any questions, I would be happy to answer.